Okay, let's start this new topic about controllability. The concept of controllability actually started to emerge at the beginning of this quarter. We actually have a canonical form, controllable canonical form that looks like this. And we have now talked about also stability. Let's make a connection and understand controllability in a much deeper way. Let's look at this example. You have a symmetric design of the mechanism, same mass, and then the spring and damping coefficients, they are all the same. And then I can apply force that's symmetric to both masses. For a single spring mass damper system, it has two states, position and velocity. If I have two mass, then I have two sets of position and velocity. So I have four states in total for this system. If it has equilibrium point somewhere here, they're both at the equilibrium point, then if you deviate a little bit from the equilibrium point, energy will decrease, and then it's going to be stable. Is this controllable intuitively? That's a different story. A system can be stable but not controllable. A system can also actually be unstable but controllable. The central concept of controllability is saying that whether you can arbitrarily control the state, and this state is all the state variables. For this system, if it has four state variables, then that means I will be able to control position velocity of these two masses arbitrarily as I want. That's controllability. And then there's this also concept of the degrees of controllability. So here it says this is control x in all the state space. So it's n-dimensional state vector. The concept of whether a system is difficult to control or not, or easy to control, it's a sub-question here. So for example, I have two inverted pendulum-like systems. I can put this pendulum to be around the equilibrium point on the top. So I can do this reasonably easy. Now, if I have this, they are the same length. This one is much lighter, and then it's significantly more challenging to put this around the equilibrium point, right? So you can see the degree of controllability. It's saying how much effort needed to do this job. In practice, even if a system is completely controllable, but if it's a motor control, if it takes 1,000 volt to control the motor to some desired position, then that's not a super helpful scenario, and the system may not be as controllable as we want. Those are the two central concepts of controllability. The system here is uncontrollable because of the symmetric design. If you apply the same force to the mass on both sides, it's symmetric. So you will always have x1 to be the same, the position of these two masses to be the same if you define the directions. So I define the direction of x1 to be to the left and x3 to be to the right. So the magnitude are the same. And then the velocity is the same. So these are always hold. You can't arbitrarily stir x to your desired location in the state space. So this is uncontrollable. But it's stable. For discrete time systems, let's work on the time invariant system case. let's say initial time, and then target time. We know for discrete time systems, it has a solution xn. It depends on the initial time, a to the power of n x0, and then the remaining is the properties of the input. Xn is going to be dependent on un minus 1. So I'm going to put I'm going to put un minus 1 here. So Xn is going to be b times un minus 1, and then you substitute, do the iteration how xn relates to xn minus 1 and un minus 2. So you're going to have a bunch of previous inputs appearing here until the start of the time. So dynamic system, all the previous inputs matters, and then they go into the state equation. So that's I'm just simply restating the state equation solution for discrete time systems. What we are interested is this. This is my target. If this is arbitrary, I want to know whether I can find my control sequence such that I can pick this arbitrary, and then I can find the solution of the control sequence. Or in other words, can I find this control sequence So the question is really, can I find this control sequence u from 0 to n minus 1 such that this equation has a solution? And on the right hand side, this one is arbitrary in the n-dimensional state space. If this is arbitrary, if this spans the entire n-dimensional space, I can always find we can always solve this solution. That means the system is controllable. Now you can see whether the system is controllable really depends on this matrix equation. And then if I say this is PD, this is a matrix, it depends significantly on the properties of the matrix PD. So let's spend some time on this. The first question is, what is the dimension of PD? If the system is, so the dimension is, if B is a column vector, okay? If B is a column vector, in other words, U is a scalar. If B is a column vector, U has to be a scalar. It's a single input system, like this, all right? If B is a column vector, then you have one column, A times B is another column, and then A to the power of n minus 1 times B, this is also a column vector. How many columns are there in here? N columns over here. So its dimension is, the number of rows is the same as the number of rows in B. So there are n rows and n columns if B is a single column, if it's a single input. If PD is n by n, what is the condition for this equation to have a solution? Rank is n, right? If the rank of this matrix is n, then it spans the n-dimensional space, right? Any vector in the n-dimensional space can be decomposed into some linear combinations of these n independent columns. This is if it's single input. If U has multiple inputs inside, if you have two inputs, then your B matrix is going to have two columns. That's the way for this multiplication to work. In that case, you still have n rows. The number of rows is the same, doesn't change. But the dimension of B and consequently all these other terms will change. If you have, I'm going to use, let's say, the dimension of U, this is the number of input you have, times n, if multi-input. So in that scenario, what is the condition for this system to be able to solve? In this scenario, you have many more columns than n columns, right? And on the left-hand side, you still have an n-dimensional vector. This equation will have a solution if I can find n linearly independent columns from this big, it's a wide matrix, right? You have more columns than the rows. If I can find n linearly independent columns from here, that means I can still be able to construct any vector on the left-hand side. So the criteria is n linearly independent columns from here. Both these two conditions, whether it's single input, single output, they can all be summarized in the same conclusion, which is you have to be able to find n linearly independent columns in this matrix PD. Or in other words, the rank of this matrix has to be n, or in further words, it has to have full row rank. It has n rows, and then if it's, the rank is n, that means it's full row rank. Then we have this conclusion over here. For this discrete time system, the controllability depends on properties of this PD matrix. And if PD has full rank, its rank is n, it's not, full rank is not accurate. It has rank n. Then it is controllable. You can say full row rank, that's accurate. Full rank itself is not accurate because it's not full column rank in multi-input case.